In this video, we're gonna build or design an active band reject filter, but what again, much like what we did in bandpass filters in the earlier video, we're gonna use what we have learned to design, that's low pass filter and high pass filter, trying to do a band reject. Just a real quick reminder of what a band reject is. A band reject filter is basically a filter that allows frequencies to go through before some value omega C1 and then frequencies above omega C1. So if you were to draw a ideal transfer function for a band reject filter and find the magnitude, that's what it would look like. You would have passband here, you would have passband here, and everything here will be rejected between the omega C1 and omega C2. So let's go ahead and take a look, see if we can go ahead and use low pass filter and high pass filter to implement that. Okay. So let's do this one at a time. So earlier we had designed a low pass filter, and a low pass filter would be and of course the feedback resistor, R low pass, and we're going to design them as a unit gain filters, and this has got to be a capacitor, of course. So we have a capacitor here, and that's the low pass filter. Great. So this is a simple low pass filter. Let's just going to talk briefly about what a characteristic of a low pass filter is. A low pass filter, basically, if I take a look over here, can implement this piece where it's going to let things go through up to a certain point and then cut everything off, and that's called the low pass. That's the definition of a low pass filter. So let's say our low pass filter is here and our cutoff frequency for the low pass filter is there. We know that that is going to be equal to 1 over RL CL. So omega C1 is the same as that, and here is our low pass filter. So we're going to use that low pass filter to implement the first part of this. Now we can also use a high pass filter. Hopefully the high pass filter we will use to implement this piece, this side of it, where omega C2 would be omega C high pass filter, which is equal to 1 over R high C high. And as from the earlier work we've done, we know a high pass filter would look like C high pass, R high pass, we got the op amp and a feedback. And since we're going for unit gain, we can make this as a high pass. Okay, now in this case we want the high pass, the blue version, and we want the black version to add up, and this, the way we add them up is by adding a third stage, which is a summer stage, add sum in terms of adding. So I can have an RI here, and I can put the exact RI in here, and I can connect these two together. And then if I'm looking for a specific gain, I can run this to an amplifier stage, and there is RF. And as we've said, the gain is going to be minus RF over RI. It gives us the gain stage. This gives us the blue gives us the high pass filter, and that, so there we have it. So now if we get these two connected, put our input in here, V in, and we get our V out here, then we have our H of S. And if you look at it, H of S is going to have a gain minus or K. Let's leave it at K. And just to make sure we are on the same page, is that the gain for K, which comes out of here, is going to be minus RF over RI. Okay, and just a reminder, the transfer function for low pass filter, the transfer function for low pass filter is H of S. For low pass filter is H of S equals to omega C low, or 1 in this case. Let's just go omega C1 for the lower frequency, and then S plus omega C2. And then the gain for the high pass, or the transfer function for the high pass filter is H of S equal, and these all have a minus on it, if you're getting to put them in there, minus S over S plus omega C2, or omega C high pass. So as we've said, as we were just about ready to do this, H of S for the whole thing, for the band reject filter, that's from output here to input here, it's going to be basically K, which is the gain that comes from here, multiplied by the sum of whatever happens in here, which is going to be minus omega C1, and this is a 1 as well, omega C1 divided by S plus omega C1 plus minus S for the high pass filter over S plus omega C2 for the high pass filter, and the whole thing is multiplied to gain, which comes from here. So this is the transfer function. After doing a little cleanup, we'll get it to the standard form, which is H of S equals to K multiplied by S squared plus 2 omega C1 S plus omega C1 omega C2, and the denominator is S plus omega C1 times S plus omega C2. It wouldn't take too much to make this look like the standard transfer function for band reject filter, which we had in the earlier work we did as part of passive filters. Now, just a refresher, omega C1 is really omega C low pass filter in here, 1 over RL CL, and then omega C2 is equal to omega C high, and that is 1 over RH CH. And of course the center frequency is omega 0 square root of omega C1 omega C2, and that's pretty much everything, and the K we know is already equal to minus RF over RL. So that is basically the band reject filter. We could also plot using Bode plot to represent a little closer characteristic of what a band reject is, but for the purposes of here, this diagram closely represents what a band reject filter does.